Yes.
Okay, welcome sir, welcome Agrawal sir. I now request Nakshatra to please welcome both of our guests. Nakshatra, are you there?
Yes, ma'am, I'm here.
Yeah, please.
Yes, good evening, everyone. It is my pleasure to welcome all of you to this insightful session on software engineering. Today, we have the privilege of learning from two esteemed experts in the field, Mr. Raghuvir Rao and Mr. Vijay Agarwal. Mr. Rao is a highly experienced solution architect with an impressive career spanning 30 years in developing Java/J2EE, service oriented applications, and cloud computing. He possesses an in depth understanding of object oriented design and development, along with strong expertise in agile methodologies, including SAFE and Scrum, having served as a Scrum Master. His vast knowledge extends to database applications, cloud native designs, data warehousing, and DevOps practices, making him a valuable resource in modern software engineering. He also has hands on experience with microservices, event driven architectures, AWS, CI CD, and production deployment strategies. His expertise in end to end software deployment, from innovation and prototyping to testing and deployment, will provide us with invaluable insights into industry best practices. We are truly honored to have him with us today. Let us make this session interactive and make the most of his vast experience. Please join me in welcoming Mr. Raghuvir Rao and Mr. Vijay Agrawal.
Yes, Raghu sir, you can.
So Raghu, let me quickly share. Let me start with the internship and hackathon, and then you can take over.
Yes.
So let me replace current share. Can you see my screen? International Hackathon?
Yes, sir.
Okay. So hello, everyone. I quickly wanted to, before we start Raghu's session, I quickly wanted to let everyone know that we are conducting an international hackathon, which is US and India. And we have a few paid internship opportunities in coming in May. It'll go over summer. And those, sorry, so everyone can mute. So everyone can mute yourself.
Mr. Karan, please mute yourself.
Okay.
Students, please mute yourself.
Hello, Rutuja.
Yes, it's creating disturbances. Please.
Okay, I'll continue. I'll talk a little louder. So, like I said, we have a few paid internship opportunities in summer in AI, ML, Java, Python, and PHP, MySQL. So in the past, we tried to interview students and then give them the opportunities. I think we did in Java and a few more. But this time we were thinking of doing it as part of the hackathon, so that way we don't have to interview, but you can showcase your skills. There would be a few sessions where some industry experts will be talking and taking some sessions on like how to pitch the winning strategy and other AI ML things, right? So let me just go to the next one here. So it's called Future Minds AI Hackathon. We still have 6 days to register. This is starting, the registration has started. I will put this link in the chat. So please feel free to register if you are interested in AI, ML, Python, Java, internships, etc. So the winning teams will be given some paid internships in May. So I'll add that link in the chat. And Monali ma'am also have this link, so she will send it again to everyone. So please feel free to register to that. Okay,
Yes.
let me stop share. And Raghu, you can go ahead share.
Okay. Looks good.
Yeah, we can see it, Raghu.
Okay. Hey, so let's get started. This talk is primarily about algorithms and also how we can apply these algorithms in our daily lives. Or usually we study theoretical aspects of algorithms, but sometimes trying to apply them to our daily lives or to real life problems may be a challenge. So this particular talk will try to address those challenges, right? 90 Yeah. About 95% of this talks is from this particular book, Algorithms to Live By. It's a very nice book written by both sociologists and a computer science engineer. So they talk about both the problems which are there in sociology versus what problems are there in computer engineering, and the intersection of both, and how an algorithm in one can be used by the other. So this kind of goes to the interdisciplinary aspect of computer science. So it's not just in coding or whatever. There are multiple domains in which algorithms and computer science can be used, or whatever is the basis, the theoretical foundations that we have in any of these things. It can be used in multiple other disciplines, right? So if you look at algorithms, right? Basically, what is an algorithm? So an algorithm is a process. It's like a mathematical problem where you can define it in multiple steps so that you can repeat it and solve this. So if you actually have an algorithm and you can apply the same principles that you have defined in that particular algorithm to solve the same set of problems, similar problems, right? Problems in the same domain, we can use that particular algorithm to solve them. So that being said, so in this particular talk, I kind of want it to be a little interactive. So I will, if you have any questions, please raise your hand and ask the question at any point in time. We'll have some like 5-10 minutes in the end to answer a few questions. If you have any questions in the end. One other thing is that I'm not going to the deep mathematical side of things, like the proof of all these algorithms, etc. Those are primarily concern of people who are dealing with theoretical computer science, etc. The talk will become too long if we go into the mathematical parts of it. And all that. And that being said, I was very, very bad in mathematics. So I'll not venture into that particular domain. Okay. Okay. Now, let's start with this particular problem. This particular problem is a pretty famous problem in computer science. This is called as like the secretary's problem. So basically, what you have to do is assume that you're a manager and you are to hire a secretary. All right, you have n number of applicants in your who are lined up for this particular position. You can interview these candidates one by one in order, right? So you interview the first candidate, second candidate, third candidate. You can interview them in any particular order. Okay. Once you decide that this particular candidate has been selected, right? So that candidates get selected, and then the rest of them go home, right? So that's the deal. And once the candidate has been rejected, right? You cannot call him back and offer him that particular position, right? Now, the problem is, what is mathematically the minimum number of candidates that you have to interview so that you get the best chance of hiring a candidate, right? So in this particular interview process, right, what we have is like the person, he will interview the person. The candidates are in any random order, right? It's not like they're ranked from the worst to the best or best to the worst. They're not in any particular order. They are in random order. And we have to decide based on this particular information, how many candidates do you have to interview, minimum number of candidates, so that you can get the best outcome, right? So this is a mathematical problem which has been worked on for multiple years. There is a mathematical solution to this particular problem, right? So in this particular problem, what we are trying to do is that you don't know the quality of candidates or what kind of candidates are there in the pipeline. So you kind of need a baseline of what an average candidate is, and that you can hire. So to get to that average candidate, right? To get to that average candidate, you need to interview a few candidates on your own. So that's your the data set which you're going to use to evaluate what is your criteria to hire. And after you have come with that particular criteria, right? You can use that criteria to go to and hire the next candidate, right? So this is this particular theory in computer science, data science is called as optimal stopping theory. So this is when you're looking to figure out what is the average the best candidate look like, how does he look like, right? You're going to interview people without hiring them. At one point in time, you'll stop that, and then what you will say that I know what I can expect from these candidates, from the pool of candidates that I have, and I'm going to interview the rest of them, and I'm going to hire the best one that the best one that I get, right? So that is the thing. So this thing, what you're doing is that you're observing all the variables sequentially, and then you decide at what point you're ready to take an action. So this is this kind of problems can be applied in multiple domains. We'll go over all these in the next coming slides, right? Theoretically, mathematically, what we have is that like 1 by E, all right, about 37% of the candidates you should be able to interview. That gives you a baseline, right? First 37%, right? If you have, let's say, 100 candidates, and you interview the first 37 candidates, and you get an idea of what the average candidate looks like. Once you get to that 37, right? Then after that, from the 38th candidate onwards, you interview, and whoever is meeting the criteria, right, of your objective, after the 37th candidate, you should be ready to make an offer, right? So that is what this particular algorithm says, optimal stopping. So let's say we can use this for hiring an assistant. This can be used in dating, right? So if someone is dating someone and they want to, how do you decide when you got the perfect partner, right? So let's say, how many people do you really date before you actually settle down? That's one set of the one domain where you can apply. And then there's like when you're buying a house, right? Say suppose you're going to buy a house or you're going to rent a house in Bombay, right? What is the minimum number of houses that you have to see before you're ready to make an offer, right? If you make an offer at the first house that you buy, right? The first house that you look at, you don't know what the other houses in the market are. You don't know whether you're getting it for the right price or the wrong price. So when do you actually stop, right? So in this, for buying a house, let's say if you have 30 days to buy a house. So if you apply the 37% rule, right, you will come up with 11 days. So the first 11 days you spend looking. Don't take your checkbook. Don't make any commitments for the first 11 days. And after the 11th day, the first house that you find which meets your criteria, you should be ready to make an offer. This is assuming that, right? I mean, once you pass on a house, right? The market is so tight that, you go to the same house 2 days later, you're not going to find it, right? So that's the problem domain where you can use 37% rule will give you the best mathematical chance of finding the best house, right? So this particular problem in computer science is called the odds algorithms. There is a mathematical proof for it. There are variations to this particular problem, right? So with rejections, what that thing is like, say suppose if we apply this to the dating problem, so you have you apply the same 37% rule, and after the 37% rule, you go and propose to someone, and they say no, right? In the case of a house, if you make a payment, you get the house, right? There is no rejections there. But in this, if there is a chance of a rejection, right, then the mathematical problem changes, right? The constraints under which this particular algorithm is operating changes. So in that case, right, you cannot wait for 37%. You have to be ready to commit earlier. So in the domain where you have rejections, this thing mathematically reduces to about 25%. So if you have you use your 25% as your first sample set, you can decide what is your optimal criteria there. And after 25%, you should be ready to make an offer or ready to propose. So in that case, you'll have the best odds. The other one is you have a recall. In recall, what you have is that, right, once you've rejected all these people, right, the constraint in the earlier problem is you cannot go back. But if you have the option of going back, right, so let's take the same secretary's problem. So if you had gone and interviewed all these people and you had passed them on the first round, right? Let's say after interviewing about 70 people, right, you decided the candidate number 40 was the best, right? You can go back to candidate number 40. In that case, right, your optimal stopping comes at about 61%. So you can interview about 61% of the candidates. And after that, any candidate that you get, you should be able to make an offer to you have your best odds of selecting the best candidate. Okay. So this one is called the odds algorithm. So if you go online, you can get, or anyone who is interested in the theory of this, you can go online and you should be able to get a mathematical proof to this particular problem. Okay. Okay. So the next algorithm we are looking at is called explore exploit. In this particular problem, right? What you're trying to do is how there is a gathering new information, right? That is called the exploration part of it, and using the existing information is called the exploitation part of it, right? So let's let's take an example for this, right? Let's say you are you're going to a restaurant, right? And your aim is that like you go to a restaurant once a month, and you want to have your best dining experience when you go out to that particular restaurant. You have a set of favorite restaurants where you go, and once you go there, right, if you eat the food, you're there, you know that you're going to be happy, right? There's no questions, everything is good. But if you have a set of, like, say, 5 restaurants and always keep going to those 5 restaurants, right? If there is a new restaurant which opens in town, right, and you will never get to experience that. Because you're always going back to those set of 5 restaurants and not trying to explore any new restaurants, your opportunities are kind of become less. Same thing you can apply to music, right? If you're listening to music, you have a favorite artist, you listen to that particular favorite artist all the time. You don't go and listen to anyone else. How are you going to get exposure to the newer music which is coming on, right? So what is that fine balance? How much amount of time should you be exploring? And exploring is trying to figure out what are the newer things to do, and the other thing is how much time should you spend on exploiting this particular this thing. So this is a good problem in computer decision data science that they are grappling with. Yeah. So what's the problem here is because, right, I mean, exploring, once you're exploring, you can you can get long-term gains, but comes at the this thing of you may not get some immediate rewards out of it, right? So let's say in business, right? Everyone, like all these businesses, they try out new products, they spend money in R&D, etc. So what is the right trade-off for how much of money should you spend on R&D and how much of money should you spend on products which are already working? You know that this thing works, you're making 30% profit in this particular business, right? And would you take like 5% of your money, 10% of your money, and put it into R&D, right? If the money you put in R&D, there is no guarantee that it's going to succeed, right? There's a good chance that you're going to fail in that particular endeavor. So what is the right, how do you maximize your profit in such a way that you're not losing any future opportunities? So that's the problem in business. Same thing, right? A doctor. A doctor for a particular kind of disease, right? A doctor knows that this medicine works, and he's 100% sure it works for his patients, so he gives that particular medicines to the patients. And there are newer drugs which come into the market. So if he doesn't try out that new medicine on the patients, he never knows that if he's passing a drug which may work better for his patients. So what is that fine balance that a doctor has to have of how much of drugs, like the medicine he gives to his the older medicine which he gives to his patients versus the amount which he gives, the newer medicines that he gives to his patients. So there is a mathematical number to that particular thing. So in artificial intelligence, and especially in reinforcement learning algorithms, you have the same exploitation trade-offs, right? If you look at it, right? Okay. If you look at it, the one thing is there are multiple constraints in this particular algorithm. Now take the same, let's take the same problem of you visiting a restaurant, right? Now, let's say you're visiting a new city, right? You're going to Bangalore, and in Bangalore, you're going to stay there for 10 days, and someone has recommended 10 good restaurants for you to go, right? Then what is your explore exploit algorithm at that point in time, right? If you're in this case, what you have is your domain, your duration is fixed. You're going to be there for 10 days. You already have 10 restaurants already lined up. There's no need for you to experiment it, right? So you don't have to spend anything on exploration. You can just exploit in the sense you can just go to the 10 restaurants which you have and go to the one, and you'll be sure that you'll come out happy out of these in all these 10 restaurants. So one of the constraints in this particular thing is the duration. The same thing for in businesses too. The horizon into which they are looking to do business, right? That will determine the trade-off between the exploration and exploitation. If the horizon is like, I'm going to be in business for only 5 more years, and then I'm going to retire after that, in that case, you don't really have to spend too much on exploration. You can just exploit the things which you know will work and make money out of it. But if your horizons are longer, all right, in that particular case, the exploitation ratios will be a little different. Okay. Sounds good. Any questions so far? Okay. Now, go ahead. Okay. If you have, just speak up if you have any questions. Just unmute yourself and speak. So let's say sorting, right? This is something all of us have learned in our computer science theory. And those problems are pretty straightforward, right? I mean, you have a set of 10 numbers or 20 numbers, and you have to sort them out. Now, let's make this a little more interesting. What you have is that if you have collection of socks, right? Let's say if you have n pairs of socks, and these socks are of different sizes and different colors. You put them in a pile. So in your this thing is you pick out one socks at a time, right? How many times would you have to pick out minimum number of socks from the pile so that you can match all the pairs, right? So that's the problem. Just to make it. So in this case, right, what you have is you have unsorted. You have, let's say the socks is colors are in, you have blue socks and green socks, and let's say 1 and 3 are the size of the socks. What you have to do is that you have to match the pair. If you were to match it, right, how would that do? how would that look like? So the first one and the fourth one, both are of size 1 and color blue, so you can match it. The second one and the last one, they are all both of size 1 and color green, so you can match them. Then the third one is third one from both ends. There are 3 in green that you can match them. So this is this is the problem domain, right? How will you be able to match these? So let's look at a couple of algorithms which we have to match these soxes, right? Are you able to, like if you're able to see it, right? So how in this particular thing, what you're doing is that the first thing is that you create an empty, you have n number of soxes, right? And then you have an answer which is like an empty, you initialize it to empty, and then you have it taken. So if you have n pairs of soxes, so the length of it will be 2n, right? So yeah, if you go through this and if you say if it is taken, that means it's already been matched, then you continue. If it has not been taken, then you set it to taken of I is set to true. Then you loop through this again. If both the soxes are the same, then you add it to the answer and set the taken to be true. And then in the end, you return the answer, right? So is this piece clear? What is this program trying to do? Is that clear? This is not really Java or basic or anything. It's just like pseudo. So what you're doing is you're looping through, right? And if you have n number of soxes, you're looping through twice, and you created an array where the answer is empty, and where whatever is matched, right? Is you put them in taken. That's like a temporary storage. Your answer is your final one. Whenever the things are matched, you add them to the answer. Okay. Can you mute? Okay.
Yeah, I muted.
Okay. So in this particular, this is one in the first solution. In this, the time complexity is n square. If I think in second year or something, you have this big O notation for complexity of algorithms, if you're familiar with it. In this, the time complexity here is n square because you're going through twice this thing. To start with, we iterate over all the soxes. For each one, we iterate over all the soxes located after that inside that array because we are going from +1. So if you look at it, it'll be the mathematical part of it is 2 into n minus 1 into 2 into n divided by 2. And that gives you the number of this thing. That gives you the complexity of this particular algorithm, right? So in the second one, right? In the second, if you're trying to sort the same thing, what you do is that you take the same thing. Your answer is an empty sequence. First, what you do is you sort them. So basically what you're doing is you're putting all the ones together, you're putting all the twos together, all the threes together. So you just sorted it. And then what you do is that you go over that. And if you pick the first one and the second one, in this case, you had two pairs, right? I mean, one was green, one was blue. Since you already sorted it, you pick the first one and you pick the second one, the chances are that it is either going to be true or false. And if it's true, you add it to the answer. If it is false, you add one more and then loop over again. And then you'll be able to get to this success, to get this. Here, the complexity of the algorithm, right, is you're looping over this array only n times, but the complexity algorithm is in the sort, right? It depends on whatever sorting algorithm that you pick, right? You will get the complexity of the algorithm will be determined by that. So you probably are familiar with this, like your bubble sort will, at the best case, it will get O to the power of n, and in the worst case, it is n square. So you have all these different kinds of sorts, which will give you all the, like you probably would have already known the complexity of each of these algorithms. It gives you a matrix of all of these. So we'll not go into the mathematics of all of this, but this kind of gives you which one to pick. And if you look at it, right, I mean, in this particular thing, if it is O of 1, then it is linear. That's the one you have in dark green. And if it is log n, that is pretty much linear. So it is in the bottom, it's in the lighter green. If it is O of n, right, as the number of elements increases, right, the operations cost also increase. So n log n is the one in the brown, and then the ones in the purple color are n square, etc. So those are like the worser algorithms. If you ideally want something in the green or light green or maybe yellow, that will give you your best performance to space ratio. So in this particular case, right, the time complexity here is n log n. This is because, primarily we use merge sort, which has the n log n. And then once you have sorted it, right, we are going over the array only once to get to the to get over it. So this one, the complexity of this thing was n log n and looping over it once. So the complexity still remains n log n. In this third case, right, we are doing the same thing, but what we are doing is that we are creating a hash set. So we go over that we go over everything, and we put that each of the socks in the hash set. And if that hash set already contains it, we add it to that, add to the answers and match it. And then we remove it from the hash set, and then go over this once more, like loop over this, and you'll get your match soxes. In this case, right, there is no, it's a direct correlation, and this hash is like it is linear. Your complexity is in the hashing function, and you go over it linear. You don't have to loop over it multiple times. So this gives you an O of n, which gives you the least complexity of these algorithms. So basically, what we are trying to say is that depending on whatever is the algorithm that you have picked, you have to pick the right one so that it gives you the best time and space complexity. So the same problem can be solved with multiple algorithms, and picking the right algorithm will give you the best optimal chances of solving the problem. Right. So let's the next domain we are looking at is caching. What is caching? Caching is like the process of storing some data nearer to where it is being used, right? So let's say if you in your computer science, right? I mean, if you're in your computers, when it has processes or data which is being stored, right? You have L1 cache, L2 cache, etc., which is there on your this thing where the computer stores things which it is working on directly in the cache instead of storing it in long-term storage, right? You also have caches on your browser, right? So like if you have images and things like that, your browser will cache that locally on your browser rather than going back to the server to get that data. So if the caching is near, right, you will be able to get your best performance out of it. So there are two things which you use to give the performance of a cache. Latency is the time it takes for you to fetch the data, and hit ratio is the amount of times where you find the data in the cache rather than going back to the backend, right? So the thing is that, right, I mean, you cannot keep everything in a cache. Your cache is going to be always smaller than is going to be smaller than the data that you have, right? In your database, you may have a million rows, right? But your cache may be only of the top 1,000 elements which are there, which you want to cache. So when you are caching, there are multiple ways to discard the element from the cache, right? These multiple policies are like the least recently used, the least frequently used. In the least recently used, basically, you put a timestamp on when that particular thing was accessed, and particular element was accessed, and you keep filling the cache. Once the cache is full and the next element comes, right, you go to the element which was least recently used. That means that had the way in the past. You take that element, remove it from the cache, and add the new element used, right? And then the other algorithm is least frequently used. It's a variation of least recently used, but instead of maintaining the time, right, you maintain a count. How many times was this particular element used? If it was used, if this element was used multiple times, and that means even if it was not in use for a long time, you still keep it, but you remove the element which has the least number of hits. Similarly, you have the most recently used. So the most recently used is the one which you can use to take it out from the cache. The other one is first in, first out. So you would just put them in a queue, and the first element comes in. That's the element which is going to go out. And then the last in, first out is you take it out and put them in a queue and just keep removing the element from the queue. Depending on the algorithm that you have, you can actually pick which one will work best for you, right? Which one is the one which works best for you. Okay, so let's see how this thing applies to our daily life. Let's say you have a closet, right? And in your closet, you have to organize the clothes in such a way that you find your favorite clothes faster, right? Is there a way is there a mathematical way that you can use to put this, to sort your clothes so that you're able to find your clothes faster? This is a variation of the caching problem that we have. So to do that, right? Let's say what you do is when you're ready to hang the laundry, right? Which is what you do is you move all the clothes to the left, all the clothes which are there already on the hanger, you move them to the left. And the new clothes that you're putting in, you start putting them on the right? If you keep doing this, then you're kind of, you're using a LRU order. So the premise here is that, right, once you put the item in in your closet, when you're looking through, you start from the right, and you keep going down, and because if you're repeating the stuff which the things that you want to wear all the time, right? What you're doing is you're doing a LRU. You're picking the element which you want to wear, use it, and after you're done with it, you move it all the way to the right. So that kind of keeps your cache of all the things which are there. And if your closet space has run out, right, the clothes which are there to your left-hand most side, right, that are the clothes which you have never worn, right? So those are the clothes which can kind of be discarded because you're not worn them in like last few months. You can take them and you can pack them in boxes, etc., and move them out so that you can make more space in your closet, which is more like a cache. Let's see if you have a variation of the same problem, right? Let's try to see if there is a variation of the same problem. Is say your constraint is not that you're wearing your favorite clothes, or you want to make sure that you're not repeated your clothes, right? You're not repeating your clothes. And so you want to store them in in your closet in such a way that you're using only like you want to pick a pair of clothes that you want to wear, but you don't want to repeat your clothes, like whatever you wore on Monday, you don't want to wear it back on Wednesday. You want to wear it back after 2 weeks or 3 weeks or whatever, right? If you were to do that, what would you do to this particular algorithm, right? I mean, instead of least recent, you used what you'd instead of hanging your clothes from the right, all the wash clothes, you would move them all the way to the left. But when you're picking, you'll start picking from the right, so that you're picking the element which has not been used recently. So you're always going back from the right. The same thing. The same problem, you can do it in office filings. Let's say that this is a office clerk, and he's working on files, right? And he has multiple files, and he's working on these files. And then the constraint here is that if there is active file, right, and then he's probably going to get more queries out of it. So he'll have to go back to that particular file more often. And the thing is that, like, some of these files, right, in some very, very old cases, and the file is there, but it's not going to be accessed very often. It's going to be accessed in very rarely. So how do you solve this particular problem, right? So in this, there's also sort of a closet problem. So you have like boxes, and in the boxes you're storing your files. The file which you used most recently, let's say in every box you're storing 5 files. So you have multiple boxes like that, all lined up from left to right. And let's say you go look for an item. And once let's say you get the first file, you take it and put it in the leftmost box. Second, third, fourth, fifth goes to the leftmost box. And then you get the next file. And if it is, you take it and put it in the second box, etc., right? So you're filling it out from left to right. And if you get a file, which then you go look through all the files from the left to right. And if it is already there in that particular, let's say you find it in the third one, third box is the file that you want to use. You pick that file out, use it, right? And then you take it, when you're replacing it, don't put it back in the third one, put it back into the first box again, and remove one item from the first, put it into the second, from the second, move it the last item, move it to the third. So that way you're kind of maintaining your least recently used item. So the files which are very active will always stay on the left, and all the files which have not been used, right, they will keep moving to the right. And then if you run out of space of boxes, all the boxes which are on the right, you can remove it and replace it with an empty box, and so you can start using them. So that is another use of this particular algorithm, right, caching algorithm. So so that's about it. Now there are multiple other domains which they have in this particular book, primarily on the scheduling and other things like that. It's definitely worth a read. And if you're interested, we can do more sessions on this. We'll get some of my friends to come and talk to you about these some algorithms like this. Okay, so that's it from my. If there are any questions, I can take them now.
I quickly wanted to say before questions, I think what I have seen is these kind of questions which Raghu covered here are asked during the job interviews and internship interviews. So what we learn in college, how do we apply when we are actually doing interviews, is several times the panel asks these kind of questions. So it's very useful. And I think the book Raghu mentioned, along with the information, hopefully that will help you guys in answering questions in the interviews. Yeah.
Yeah. Okay.
Any questions? Anything anyone wants to add? Maybe not even a question, if you have any feedback or comments. Okay, if not, let me again mention, as I said, we continue to do more practical sessions for students. And as I said, artificial intelligence, AI, is very much now a lot of things happening there. And a lot of our friends and organizations have internship opportunities. So please feel free to ask questions. You can send it to Monali ma'am. She can send it to us.
Yeah.
And also, yeah, I think as I mentioned, feel free to register for the hackathon, which is happening next month, so that you can, maybe if you win, you'll get some internship opportunities. Raghu, any last point you want to mention?
Yeah, nothing much. If there is any questions, okay, there are a couple of questions in the chat. I'll take a look at it. Okay.
Hello.
Yeah.
Students, any questions from your side?
So
Yes.
there is.
If any questions, you can also post it in the chat box.
Yeah, there was one question: how the least recently used algorithm can be used to organize office files. We talked about it. So same thing, put them in boxes, move them from left to right. Always use the least recently used, keep it to your left, and as you see the things which are not being used will slowly start moving to the right, and then you'll be able to use that in your filing, use that as your this thing. So keep the clear thing is, right, I mean, if you pick a file, right, you don't put it back in the same place where you found the file. right? If then that you don't get your least recently used. So once you use a file, you have to put it back into the top of the queue again, and then move all the elements one to the right. So if you keep doing that, you'll get your least recently used algorithm automatically worked out. If you put them back into the same place, then it's gone. Then the order is gone. You don't have a notion of when it was used. So if you know, if you start putting them always to the left, the recently used, you are guaranteed to know that the stuff on the left was used recently, and the stuff on the rightmost side, right, it was not used at all. I mean, it was used long time ago. So that kind of helps you solve this particular problem, right? Any other questions?
Yes, any other question, student? Anyone? Sir, any questions in the chat box?
Okay.
I do not, do you see, Raghu? I mean, I'm not seeing anything.
What are the different caching policies discussed and how they are applied in real life scenarios? Like, okay. Yeah. So depending on what the constraints are, right? I mean, organizing a closet. If you want to wear your favorite clothes all the time, then you put all the clothes in your closet and hang all the clothes that you are interested in. Once you wash it, take it out, put it on the rightmost side, right? So. And when you're looking for your clothes, start from a right and keep going left. Because the stuff which you have used recently, chances are those are going to be your favorite. You're going to pick that. And once you pick it, you wear it and wash it and then put it back almost on the right-hand side. So that kind of gives your, in that particular case, you're using your least recently used. Here what you're doing is what you're optimizing for is finding your favorite clothes fast, right? And if you don't want to optimize for finding your favorite clothes fast, like you are a fashionista, you don't want to repeat your clothes, right? Whatever you wore on the Monday, you don't want to wear it for 2 more weeks, right? In that case, you don't really need anything. All you need is a queue. So you put your clothes right in the same order. Put them in from right to left. Whenever you wash them, pick from the rightmost side, and when you wash them, put them on the leftmost side. So in that case, you're just maintaining a queue, and from the queue, you're taking it and using it. So you can organize your closet that way. So basically, it's the same closet problem, but depending on what you're optimizing for. Do you want to wear your favorite clothes all the time, or do you want to make sure that you don't repeat your clothes, right? Yeah, in that, depending on what your constraint is, you're picking the algorithm. In one case, you're using a least recently used algorithm, and in the other case, you're using a last in, first out. So in that case, you're optimizing for not repeating your clothes. Okay.
I think
Any
we are
more questions,
also
student?
we almost 1 hour. So if one or two more questions, we take that. If not, there is, okay, go ahead, Raghu, there is one more.
What is the trade-off between exploration and exploitation in business decision making, right? So okay, there are in this particular thing, right, there are multiple factors which are there in this particular exploration and exploitation thing. One is Jeff Bezos, right? He was working as a stockbroker in a company called D. Shaw, right? And then he told his boss that he wanted to start a bookstore online, right? And his boss was not kind of very encouraging to that particular thing. And then it said that he went and thought, he thought about it a lot. And he told, like, would I, after 50, 60 years, right? If I, would I regret this? Not starting a bookstore online, would I regret this? So if the answer is, then he thought that, yeah, I have all the comforts right now. Let me take this. Let me take a shot at this bookstore. So that's when he started this Amazon. So there, in that particular case, right, what it was the minimization of regrets at the end of the end of your life, right? I mean, you have is there are multiple decisions that you make in life, and some of them you regret, and some of them you kind of um, um, you regret not doing them, right? So, would you regret not doing this at the end of your life, right? I mean, that was one of the decisions that he used to make his decision. A minimization of regret could be one thing to make your business decisions, right? And the second thing is like, let's say if you have all these movie franchises, right? Fast and Furious 1, Fast and Furious 2, 3, 4, 5, 6, 7, right? And then you have Toy Story 1, 2, 3, 4, 5, right? I mean, you have multiples of these franchises. And then a movie studio, right? It knows what the people are ready to pay money for, right? It can keep making these movies all over again. It can do a Fast and Furious 10, 11, and people will still go and watch it, right? So in that case, it's all it's doing is exploiting. But if it doesn't want to get into a new genre of movies, right? I mean, is it ready to go into to like fantasy or horror or whatever, or comedies or whatever? So if it is ready to explore a new genre, right, then it is exploring what will work. And in exploiting, it is just taking whatever it knows is going to work and is going to make more money out of it, right? It's going to do that. Same thing in any manufacturing thing, car models, right? Do you keep making the same car over and over again, or and make some money out of it, or do you introduce newer models into the market, right? Newer kind of vehicles, newer models. So you had to kind of use that as a trade-off in making these business decisions, right? So hope that helps. Minimization of regret could be one of them. The other thing is also the constraint. How long do you want to be in business? The horizon that you have for your this thing. Are you going to be in business for 5 more years, 10 more years, or are you looking to be in business forever? So that also will help you make your decisions. If you're going to be there for a fixed duration of time, no point in exploring. Just do exploitation. Exploit whatever works for you. If your horizons are longer, then have a good mix of exploration and exploitation. Okay. If you have anything more, just send them over to Manali ma'am. She will pass it over to me and Vijay, and we will take a
Yes,
shot at answering them. Okay.
yes. Namrata ma'am, we can conclude the session.
Yes, ma'am. Nakshatra, will you please conclude the session and deliver vote of thanks?
Yes, ma'am. As we come to the conclusion of this insightful session, I take this opportunity to extend our heartfelt gratitude to Mr. Raghuveer Rao and Mr. Vijay Agarwal for gracing this event with their presence and sharing their invaluable insights with us, as well as informing us about the Future Minds AI hack. A sincere thank you to our esteemed faculty members, organizing committee, and each one of you present here for making this event a success. Your presence and participation have truly enriched this session. Thank you.
Hello.
Yeah, Manali.
Yes, Vijay sir. Should we end the meeting?
Yeah.
Yes, sure.
Yes.
Yeah,
Any
I think
questions from the students? I will forward to you.
Okay.
yes, please do.
Sounds good. Thank
And
you.
also, oh, sorry, Raghu. Yeah.
Go ahead.
Also, let us know if there are any other practical sessions or
Yes.
any of our professional expertise students want as they go into the final year and maybe internships and jobs. We would be happy to do that.
Yes, sir. Yes, yes. Sure, sure. I will have a touch with you again.
So, thank you so much. Thanks, students.
Thank you, Raghu
Have a
sir.
good weekend.
Thank you so much.
Yeah.
Bye.
Yes.
Thank
Thanks,
you, sir.
everyone.
Share the recording of the same with me so that I can share with the students.
Yes, I'll send that.